So, we start with the new lecture, and what we will do is that we will first review the last lecture, because this lecture is nothing but continuation of the previous lecture. So, now where did we start? We started with the analytical treatment of frequency dependence of various polarization mechanisms. So, if you go to previous lectures, now previous lectures, what did we discuss was, if we go back a few slides, what we had was, we started treating this. Okay. So, we started with this case of electronic and ionic polarization, where we treated this charged dipole as a linearly oscillating mechanical dipole, or linear mechanical oscillator. Now, here whether you have atom sitting here or a group or a so in case of electronic system, so suppose this is the picture. Now, this is the center of, let us say, positive charge, this is the center of negative charge, and the center of positive and negative can be treated as a positive, negative and dipole. So, this is at an atomic scale. Now, you can have at lattice scale, where you have a system like sodium chloride. So, you have a lattice like this, and here you have, let us say, sodium atom, here you have chlorine. So, positive, negative, and this also makes a dipole. So, you can treat these two systems like a mechanical oscillating system, and here if you write, you can write an equation of motion for both of these systems, where the force which is due to applied field is equal to various forces which are then generated as in turn. Now, this applied field is AC in nature. So, you have an acceleration term, followed by you have a friction term, which would be true for any system if damping is present, and then you have a spring constant related system, where which is called as spring restoring force. Now, this is because we have considered the dipole like a spring. Okay. So, and when you do analysis, when you put in the value of E is equal to E naught exponential I omega t, which is a alternating electric field. So, correspondingly the displacement for this field should be x is equal to x naught exponential I omega t, and when you make the when you replace the value of E in this expression, you get an expression for x, and the expression for x is, so you calculate various things, dx by dt, d2x by dt square, etc., and the expression for x has a frequency dependence. As you can see, what we did from this x was to calculate the dipole moment, and this dipole moment would be nothing but product of charge multiplied by the distance, and this gives you this can give you the polarizability, which would be pertinent to electronic or ionic mechanisms, because that is dipole moment is equal to alpha into E, and from this we work out what is polarizability. And here we see that polarizability has a frequency dependence, very clear frequency dependence, and it is also complex in nature. Now, given the fact that this is complex in nature, your dielectric constant is going to be complex in nature. As a result, we can explain and also polarization and susceptibility, all of them are going to be complex in nature. And if you define this susceptibility as epsilon r star minus 1, given that it is a complex quantity, you can work out the static part of the dielectric constant as 1 plus n q I square divided by m I star epsilon naught, and this frequency dependent term. And in the dielectric constant versus frequency plot, these two peaks which occur at high frequencies at let us say 10 to the 15 hertz and 13 hertz, these are the regions where resonance occurs, which means the oscillation of dipole is in resonance with the applied field. So, both of these things match with each other, and that is where loss becomes maximum, and this can be very nicely seen in the plot. So, this epsilon star can be broken down again into epsilon prime and epsilon double prime, and when you plot them versus frequency, you see a resonance term, resonance at an omega naught, which is the characteristic frequency related to either ionic or electronic, and this omega naught is going to be higher for electronic than for ionic. And so, you see a loss term, maxima in the loss at this characteristic frequency, and this is true for both the mechanism. And so, this was the analysis based on AC field, and from this then we worked out, and from this you can also get the same term that you obtained in case of simple analysis that we did earlier in order to work out the polarizability, and that if you do by treating omega as root k by m, you can make it look equal to get the same expression 4 pi epsilon naught r naught cube. So, basically what we did has been correct so far, because you can make both of these, because you can make this AC equation converge into the simple equation that we got earlier. So, then in the last lecture we started doing dipolar polarization, which is about the materials having permanent dipole moment. So, what happens in such a situation is you have a dipole like this, and this dipole, let us say, has a dipole moment in this direction, and this is, let us say, position 1, and when you apply field, let us say in this direction, field is in this direction, then this rotates itself in the direction of applied field, and this is now its new position. Okay. So, this is position, this is 2. So, in order to move from position 1 to position 2 and then back to some other position which is equivalent position, this requires this phenomena is called as relaxation. It is not just short range movement, just like in case of electronic ionic dipoles. It is like hopping from one equivalent position to another equivalent position. So, as a result, the energy versus time plot can be plotted in terms of various potential energy wells, where the molecule groups of molecules or molecule changes its position from 1 to 2 to, let us say, 3 and so on and so forth, and each time when it does it, let us say from going from 1 to 2, it has to overcome an energy barrier, and this is the activation energy which is required for migration. So, this is like diffusional process in nature, and this process is called as a relaxation. Molecule relaxes into new statistically equivalent position. So, and since this is diffusional in nature, the masses of entities involved is much more higher. The frequency at which this process happens is significantly lower as compared to the characteristic frequency for ionic or electronic polarizations, and this happens to be in the range of megahertz or so. And as a result, the way polarization develops is, so when you plot the polarization as a function of time, you have an instantaneous development of polarization component, which is nothing but sum of ionic electronic, because you know that electronic ionic mechanisms are extremely fast. So, that is why this term becomes more or less instantaneous, followed by slow development of polarization to a value which is saturation polarization, and that is the polarization when all the dipoles align themselves to the direction of applied field. Because when you apply field, now field is time dependent. Okay. Not all the dipoles respond to the frequency of applied field at the same time. That is why dipoles take their own time to align in the direction of applied field. As a result, there is a time dependence of dipolar polarization until it saturates into PS. So, now this rate of change of polarization can be expressed mathematically. So, you get an expression for rate of change of polarization, dP by dt is equal to 1 over tau Ps minus P dt. Now, this is the expression which I have given you without any derivation at this point of time, but in order we can derive this, and that is what we did last time. So, for that you choose a model which is called as a bistable model. So, what you do is that you consider this hopping model from site 1 to site 2, let us say between two sites hopping is taking place, and this is characterized by this energy barrier, let us say E or EA, whatever you call it. And so, what we have is the dipole goes from position 1 to position 2 upon application of electric field. And so, what happens is, when you consider this model, when let us say there is no electric field, and if you have this potential well, it can hop in this direction, it can hop in this direction. So, there is a finite probability of hopping in both the directions, and this hopping probability or jump probability can be written as A exponential minus E A by kt, following Maxwell-Boltzmann statistics. And when field is 0, then of course, the net probability of jump in either direction is equal to 0. As a result, you do not get any polarization and thermal effects dominate. Now, when the field is large enough, then potential energy well tilts on one side, let us say. So, depending on the direction of applied field. So, what happens is that the energy barrier on one side becomes smaller and the energy barrier on other side becomes larger. So, for anything to jump from this side to that side, it has to now overcome a large energy barrier, and for anything to hop from this side to that side, it has to overcome a small energy barrier. Now, this change in the potential energy well configuration results in what we call as change in the jump probability. As a result, you have net accumulation or depletion of charge at one particular site. So, you have a change in the charge. So, you can write the changed probabilities as F12 can be written as F into 1 minus mu E by kt, and second can be written and 2 can be written as F into 1 plus mu E by kt. So, you can see that now this was if you just wondering why it is like this, then what has happened is so this is nothing but the probability factor multiplied by another factor 1 minus mu E by kt, depending upon the application of electric field, and this mu E is nothing but the energy, and this and you can get the same now this you can relate to, if you remember what we did in case of derivation of ionic conductivity. In ionic conductivity also we took a model like this, hopping model, and there also we worked out the polarizabilities probabilities of jump. So, if you are wondering where these expressions come from, just go back to that module, which is module number 3, and look how we worked out the probabilities of jump upon the application of electric field in both the directions, and how we arrive at these expressions. So, as a result, you have change in the number of dipoles at site 1, and this, since because the probabilities are unequal, if that is true, then delta n1 dot can be defined as outflow to site 2 plus inflow to site 1. So, so outflow to site 2 can be given as minus, because you are losing charge at site 1, and what is coming into site 1 is inflow from site 2 to site 1. So, that adds. So, as a result, you have d n1 by dt as minus n1 f12 plus n2 f21, and we know that n1 plus n2 is constant, which is equal to capital N, and from this you can also write d n1 by dt plus d n2 by dt, net change is equal to 0. And then we proceeded on further to work out what half of d n1 minus n2 by dt was, and then finally we derived it, we put it into a expression for polarization. Now, polarization can be written as Pt, polarization as function of time, is equal to n1 minus n2, which is the change in the number of charge or charge density at that multiplied by the dipole moment, and then so n1 minus n2 becomes equal to p by mu. P is nothing but time dependent polarization. So, you can write it either P or P dt or Pt. So, this expression that we wrote earlier, if you make that replacement, it becomes 1 over 2 mu dp by dt to be equal to minus f divided by mu p plus E n mu E by kt. Now, now if you make proper rearrangement here, what you get is 1 over 2 f into dp by dt plus p. If you take this on the left hand side, this term on the left hand side is equal to n mu square E by kt, and this you know what it is. This is nothing but your dipolar polarizability, and 1 over 2 f is defined as, because f is probability in second minus 1, this is tau, which is the relaxation time. Okay. So, tau dpd by dt plus pdt is n alpha d e. Okay. So, this expression n into e. So, you know, n mu square e by kt becomes m alpha d e. So, you can relate what is mu here. Mu is alpha is mu square by kt, and this is nothing but your saturation polarization when all the dipoles are aligned in the direction of applied field. And so, you get an expression tau dpd by dt plus pdt is equal to Ps, and this is what we proposed earlier, that pdt was dpdt by dpt rate of change of polarization was equal to 1 over tau into Ps minus pdt. So, we get back to same relaxation equation that we proposed earlier. Again, this explains what we did earlier, and the sum of now P instantaneous can be taken as sum of Pi plus Pe, and that can be defined as P infinity, and when and this would be in the high frequency range, typically higher than 10 to the power 11 hertz, and the susceptibility corresponding to this would be chi infinity is equal to epsilon r infinity minus 1 divided is equal to P infinity divided by epsilon naught E, which is simple. I mean, because you know that chi is nothing but ratio of polarization to the displacement due to applied field in vacuum. So, now between the low at the low frequencies, you can write similar equation as epsilon rs minus 1, which is the chi, is equal to P infinity plus Ps divided by epsilon naught E. Okay. So, epsilon rs becomes 1 plus P infinity plus Ps divided by epsilon naught E, and then epsilon rs minus 1 becomes equal to Ps plus epsilon r infinity minus 1 epsilon naught E divided by epsilon naught E. So, you can jumble this around, and then what you get is Ps is equal to epsilon rs minus epsilon r infinity. So, where epsilon rs is the low frequency static dielectric constant, which corresponds to ionic and electronic. Excuse me. Yes. So, this is your low frequency dielectric constant, static dielectric constant, which combines dipolar, ionic and electronic, minus the epsilon r infinity, which is the high frequency contribution, which is only due to ionic and electronic. So, the difference of these two will correspond to the dipolar component. Okay, that makes sense. So, when you make the substitution of Ps into the expression of in the relaxation equation, what you get is tau dpd by dt plus Pd is equal to Ps, as we know, is equal to epsilon rs minus epsilon r infinity epsilon naught E. Now, what we do is that we make a substitution for electric field, that is E is equal to E star E naught exponential I omega t, and since field is a complex quantity, you would notice that many of these things have got these stars as a superscript, and this star is nothing but a symbol of complex nature of the quantity. So, when you make this substitution, then let us assume now solution of this equation is pretty complex. So, we assume that the solution of this equation was Pd star was equal to epsilon naught epsilon r star E star plus epsilon rs exponential of minus eta t. So, there is another term this that comes into picture, and then we took what is dpd star by dt now when the solution, if the solution is like this, then what we want to do is that we want to calculate dpd by dt, and we put the Pd, and then we want to relate, then we want to substitute back and calculate some quantities. So, dpd star by dt will become epsilon naught epsilon r star d by dt of exponential E naught exponential I omega t plus epsilon rs d by dt of exponential minus eta t. And then you do this further, what you come about is epsilon naught epsilon r star I omega E star minus eta epsilon rs exponential of minus eta t. And so, finally, when you make the substitutions, what you come about is tau multiplied by epsilon naught epsilon r star I omega e star minus eta epsilon r s exponential of minus eta t. This is one term multiplied by tau, and this another term epsilon naught epsilon r star e star plus epsilon r exponential of minus eta t is equal to epsilon r s minus epsilon r infinity into epsilon naught e star. So, you got some real terms, some imaginary terms, and what now we will do is that we will now differentiate this equation. So, what we will do is that we will just go back here. You must be wondering what eta was. So, here eta is some coefficient, okay, which is to be determined by the solution. So, we do not worry about it at the moment. So, now this is where we ended. So, now we have to what we have to do is that we have to separate the real and imaginary parts from this equation. So, you can see what the real and imaginary part in this equation are. This is a real part, this is a real part, and this is imaginary, this is imaginary, and this is imaginary. So, whatever is underlined is imaginary, whatever is rounded is real. So, when we separate these parts, so what you get is minus of tau epsilon r s eta exponential minus eta t plus epsilon r s exponential minus eta t is equal to epsilon r s minus epsilon r infinity multiplied by epsilon naught e star minus of tau epsilon naught epsilon r star I omega e star minus of epsilon naught epsilon r star e star, and then again make the substitute, then again make some of the just jumble up this equation again. So, what you get is minus of tau epsilon r s eta plus epsilon r s exponential of minus eta t is equal to epsilon r s minus epsilon r infinity multiplied by epsilon naught e star and minus of tau epsilon naught epsilon r star I omega e star minus again of epsilon naught epsilon r star e star. So, this is so now we need to make now we are coming close to the solution. Okay. So, which means if we want to solve this, then the both sides so this is new lecture. So, we are starting today. So, so both sides of previous equation should equal to some constant, and what would that constant be looking at the equation? If you look at these equations, the only constant, if they are equal to a constant, the only constant can be equal to 0, and that is nothing but 0. So, if we do that now, so first take left hand side of the equation. If we go back to the left hand side of the equation, which is minus tau epsilon r s eta plus epsilon r s minus tau of epsilon r s eta plus epsilon r s multiplied by exponential of minus eta t is equal to 0. Now, this naturally gives you okay, and from this you can work out what is eta is equal to 1 over tau, okay, or rather just to make it simpler, you can write it as so this epsilon r, of course. So, minus of tau eta plus 1 is equal to 0. So, this side and eta becomes equal to 1 over tau. Okay. So, this is the first. So, you get an now you get a hang of eta. What eta is? Eta is nothing but it corresponds to 1 over relaxation time. So, the units of eta would be in second minus 1. So, it is something like frequency or characteristic frequency, and from now use right hand side. So, using right hand side, if you look at the right hand side of the equation, which was epsilon r s minus epsilon r infinity multiplied by epsilon naught E star minus of this and minus of that. So, when we take this now, so this becomes equal to epsilon r s minus into epsilon naught E star minus of tau epsilon naught epsilon r star into I omega E star and then minus of epsilon naught r star. This is equal to again 0. Okay. Now, what is P d star? Now, what is epsilon naught epsilon r? This is nothing but imaginary side of P d star. So, this is okay. So, we can use the imaginary side in the imaginary side because this is imaginary. So, we can make this as epsilon r s minus epsilon r infinity multiplied by epsilon naught E star to be equal to I omega tau. So, this and this and this will make P star plus 1 multiplied by P d star. Okay. Or you can change it as or P d star in that case will become epsilon r s minus epsilon r infinity multiplied by epsilon naught E star divided by 1 plus I omega tau. So, you must be wondering why did we write this? This we are able to write because this side that we have taken is the imaginary side, and if you only take the imaginary side, then the imaginary component of P d star is epsilon naught epsilon r star E star. So, we can write this P d star as epsilon naught epsilon r star E star. Okay. It's perfectly logical in that sense. So, now we combine real and imaginary parts, and what we get is an overall expression of P d star, and this overall expression of P d star now becomes epsilon r s. So, if you go to previous equation, so the expression was P d star was epsilon naught epsilon r star E star. So, this is the imaginary part, this is the real part, epsilon r s exponential of minus eta t. So, now we are making the substitutions for each of these things and writing an overall equation. So, this is the imaginary. So, we have worked out what imaginary component would be and what the real component would be. So, if we put them together, what we get is epsilon r s into exponential of minus of t by tau. This term is time dependent decay term plus another term which is the AC, which represents the AC behavior, which is epsilon r s minus epsilon r infinity multiplied by 1 plus I omega tau into E star, and this represents your AC behavior. So, you got these two terms. Just to take it further. So, now what we can do is that we can also separate the time dependent and time independent part from the dipolar polarization, that is the electronic and ionic polarization parts. So, how we do that? So, this epsilon r star minus epsilon r infinity will be equal to P d star minus of epsilon r E star. Now, since we know that so, this is the difference, just to separate out the time dependent and independent part. So, this is the total dielectric constant complex minus the static dielectric constant at high frequencies, that will be sum of your dipolar contribution complex divided by E epsilon naught E star, and P d star we know is this, the complex part of P d star. So, what we can write is so then now we can write epsilon r star minus of epsilon r infinity to be equal to epsilon r s minus of epsilon r infinity divided by 1 plus I omega tau, or omega tau. Now, this is the complex form dielectric constant. So, we know that epsilon r star can be written as epsilon r prime minus of I epsilon r double prime. If that is true, then since this can be written like that, so we can break this up. So, if this can be written in this form, then we can break this epsilon r star into epsilon r prime, epsilon r double prime. So, epsilon r star is equal to, as we know, is epsilon r infinity plus one plus I omega tau I multiply and divide by 1 minus I omega tau, and this becomes 1 plus omega square tau square, as I square is equal to minus 1. So, I take the real and imaginary parts out. Divided by 1 plus omega square tau square, and then minus of I omega tau into epsilon r s minus divided by 1 plus omega square tau square. So, now it is easy to separate out. We know that epsilon r star is equal to epsilon r prime minus epsilon r double prime. So, we can write this as, so epsilon r prime would be equal to epsilon r infinity. So, this is the static high frequency part plus epsilon r s minus epsilon r infinity divided by 1 over omega square tau square, and this is your contribution which is coming from the dipolar part, and this is the net dielectric constant, and epsilon r double prime would be epsilon r s minus epsilon r infinity multiplied by omega tau divided by 1 over omega tau square, omega square tau square. So, this these are very fundamental equations which show direct dipolar contribution very explicitly, and these are called as your Debye equations. These are fundamental equations in for dielectric materials showing dipolar behavior. And from this you can also determine what is loss tangent. So, loss tangent can be written as tan delta, and what is that? As you know, that is nothing but epsilon r double prime divided by epsilon r prime, and this will be, you just have to make a division here, and this would be equal to epsilon r s minus epsilon r infinity multiplied into omega tau divided by epsilon r s prime minus of epsilon r infinity, sorry, plus of epsilon r infinity into omega square tau square. So, you just have to work this way out. Okay. So, this is your loss tangent. Now, if you want to plot these, this is it's interesting to plot these equations. So, let us say, so if you plot just the dielectric constant first versus frequency. So, this goes as something like this behavior, and this frequency corresponds to 1 over tau, and so naturally this part would be epsilon r s and this part would be epsilon r infinity. Okay. If you plot the correspondingly epsilon r double prime plot, this plot goes as with the maxima at a frequency 1 over tau, and if you plot tan delta, correspondingly its peak is a little bit shifted towards higher frequencies, and this is your, and this corresponds to epsilon r s divided by epsilon r infinity to the power half divided by tau. Okay. So, this is these are the, so you can see that this curve looks very different from the curves that we look for ionic and electronic polarizations. You do not have a resonance term, rather you have a relaxation phenomena here, the dielectric constant falling from a static value r s slowly around a value slowly to epsilon r infinity, and this phenomena happens at low frequencies. Correspondingly, at a frequency 1 over tau, you have a maxima in epsilon r double prime, and correspondingly you can also have a maxima in tan delta, which is slightly shifted to higher frequencies as a result of the expression that you get. Now, these equations are extremely important equations from the point of view of fundamental understanding of dipolar polarization or polarization mechanisms, and you should go through this analysis a little bit more carefully to understand what is happening. So, as you can see, so if you now draw the, so you have three pictures. You have dielectric, you have polarization, which is composed of electronic component of polarization, ionic component of polarization, and dipolar component of polarization, and all these three have different behavior. On one hand, where Pi and Pe are extremely fast, make almost instantaneous polarization, and they happen at very high frequencies. So, as a result they become almost instantaneous. In contrast, PDs are time dependent phenomena which happens slowly. So, development of saturation polarization is relatively slow as compared to these two. So, as a result you have this behavior which goes as, so it develops into PS a little bit slowly. From Pi to Ps it takes a bit of time, and as a result of this you have, when you plot dielectric constant, it goes like this through a frequency 1 over tau, and or if you plot omega versus tau, if you plot frequency it is 1 over tau, but if you plot omega tau then it becomes equal to 1. Okay. So, depending upon which book do you follow, it depends. In some books they use on x axis omega tau, and in some books they use omega. So, when you have omega, then this inflection point is at 1 over tau. When you use omega tau, then the inflection point would be at 1. So, this time dependent behavior is a characteristic of dipolar materials, which have which again happens because of inability of dipole to move instantaneously with the applied field, since the mass of the entities involved here is much higher. So, and what it means is that at omega is equal to tau, the charges are coupled together with the applied field and absorb maximum energy. So, as a result the losses are maximum at tau is equal to 1 over tau. Okay. Omega is equal to 1 over tau, I am sorry. And this phenomena, since it is a time dependent phenomena, but it is also a temperature dependent phenomena, this tau has a relation tau naught exponential minus q a by k t, and this is kind of Arrhenius relationship, which means there will be a shift in tau as you change the temperature, and this has a dependence on the activation energy. So, when you plot, for instance, that tan delta versus frequency, then the shift, the maxima that you observe, this maxima shifts to higher frequencies as you increase the temperature. So, this is increasing the temperature, and this you would expect, because as the temperature increases you provide thermal energy to the system, and when you provide thermal energy to the system, the relaxation time should go down, which means this maxima, if tau goes down, this frequency omega, let us say omega max, will shift towards the right, which means relaxation will occur much more faster, and as a result this peak in the tan delta will, or loss will, shift towards higher frequencies. So, this is this explains the Arrhenius or diffusional behavior of the relaxation time in dipolar materials. So, this is typical behavior, for example, for glass ceramics. If you want to go through some more plots, I would suggest for a few plots on I would suggest you go to the book of Hench and West, Principles of Electronic Ceramics, and this gives a very nice explanation of the temperature dependence of relaxation time. So, now as you have seen that the peak in the maxima shifts towards right on the frequency plot as the temperature is increased. You can also plot this f max, log of f max versus, and as you can see that this would be as the temperature is, so this is your high temperature side, this is your low temperature side. So, at higher higher temperature you will have f max occurring at higher frequencies, whereas at lower temperature f max will occur at lower frequencies, because the relaxation time will be larger at these frequencies. Okay. So, the complete picture is now rather different, or it looks pretty much complete now. So, the overall behavior now is, you have, if you now go from, so this is omega, this is epsilon r prime. So, you have epsilon r coming from epsilon r s going through relaxation, Okay. Then it goes through resonance, another resonance. So, this will be your dipolar component, this would be 1 over tau and relaxation frequency. This is your omega naught I, this is your omega naught E. So, here you have, in this you have ionic polarization, here you have electronic, and this is your 1 or n square. Okay. Oh, sorry, 1, just 1, as if no dielectric was present. And correspondingly, if you plot the loss, all of these go through a maxima. So, this is 1 over tau, omega naught I, omega naught E, omega, and this is epsilon r double prime. So, you can see now the presence of various features in this dielectric constant versus frequency plot, and the loss versus or the imaginary part of dielectric constant, which represents the loss versus frequency. The thing to remember is for ionic and electronic mechanism, the inflection these are resonance dependent mechanisms. As a result, the resonant frequency is on higher sides, greater than 10 to the power 11 hertz in most cases. And for ionic polarization, since it's for the dipolar polarization, since it is a time dependent phenomena, it's a relaxation kind of phenomena, and the relaxation frequency happens at much more smaller frequency, because it takes a bit of time to for dipoles to relax, because they are heavier than just 2 ions and or an atom. Okay. So, this sort of completes very important part of this module, where we looked into the frequency dependence on the dielectric constant, considering ionic, electronic and dipolar mechanisms. If you want to read about interface mechanisms, it is a little bit more complex and beyond the scope of this course, but if you want to read, you can again follow the book of Hench and West, and where which is given in some detail. So, otherwise, we have completed the important segments of this phenomena. In the next class, what we will do is that we will look at some other methods which are used to characterize the dielectric materials by using the same dielectric data, and can be used much more effectively to represent the behavior of dielectrics much more easily. And finally, we will look at some of the breakdown mechanisms of dielectric materials in the same module. Okay. Thank you.